cycle is conducted on steam as follows. The evaporator, that means the boiler, produces dry saturated steam at 10 bar. So this will be your boiler pressure. Then the steam is then expanded isentropically or reversibly and adiabatically in a turbine to 1 bar. So this would be the condenser pressure. Then the exhaust steam is partially condensed and then compressed back to 10 bar based on the pump. Now, as a result of the compression, the wet steam is changed completely into saturated water. Now, assuming a flow rate of 1 kg per second throughout, and find the condition and specific enthalpy at each point in the cycle. Then calculate the energy transfer efficiency is correctly predicted by the expression of 1 minus T cold over T hot. Okay, so the first thing is our Carnot cycle. So this would be your Carnot cycle. And this would be the boiler pressure, saturation dome first, remember, saturation dome. Then based on this, you have your high pressure, that is the boiler pressure of 10 bar, this should be 10 bar. And then the next pressure line will be based on your condenser pressure, that is 1 bar, okay? So from the table, from the property table, when you look at it, this will be your saturation pressure, saturation temperature, the specific volume for dry saturated steam, saturated liquid internal energy, dry saturated vapor internal energy, and the H here stands for enthalpy, F, subscript F here is saturated liquid, G is dry saturated vapor, HFG is Hg minus Hf, S is entropy, F is liquid, G is dry saturated, SFG is Hg minus your SF. So dry saturated, all these represents the dry saturated properties. And these with the F here, they are the saturated liquid. So this is your saturation temperature. Okay, HFG is Hg minus Hf. Or SFG is Sg minus Sf. And if you want to find UFG, you can take Ug minus Uf. Okay? So based on 1 bar, okay, the condenser pressure 1 bar. So what we have is the HF, HFG and Hg, okay, the 1 bar, and then the entropy. Okay, so this line here refers to the dry saturated steam line or dry saturated vapor line. This line here refers to the saturated liquid line, that is the F, and this is the G. Yeah. So based on pressure 10 bar, because your boiler pressure is 10 bar, your condenser pressure is 1 bar. So based on 10 bar, so these are the data that you can extract. Okay, so based on 10 bar, you have the enthalpies and then you have the entropies. So most of the time we need enthalpy and entropies only. So what we have, okay, then we simplify it by placing it into the table that I have prepared here. So with the pressure 1 bar, 10 bar, saturation temperature, write it down, 99.6, 179.9. HF, okay, based on 1 bar and 10 bar, HFG, Hg, SF, SFG, and Sg, based on these values here, which I have, okay, highlighted here. So fill up this table here. This is the first step you do, okay? So draw your table, draw your TS diagram, sorry, and then the table, okay? Place in all the properties based on the 2 working pressure. So again, This will be your schematic diagram. Schematic diagram showing you the boiler, turbine, condenser, and feed pump. So you can draw it like this, basically as a skeleton diagram, which we call it as schematic diagram. So you have your point 1 to 2 here that is based on your boiler, and then point 2 to 3 that is based on your turbine, then point 3 to 4 that is based on your condenser, then point 4 to point 1, okay, that is based on your feed pump. Okay, so the first one, we start with state point 1. Okay, so what we need is, okay, we have proven that if we were to continue or if we were to calculate the enthalpy at each point as what is stated in the question, they ask us to find out the energy or the enthalpy, okay, at each state point. So we move from one point to another. So you just use this step-by-step manner, okay, to solve other problems in power plants as well, okay. So state point 1, where you have, this is all sitting on the saturated liquid line. So this is HF. H1 is equals to HF, saturated liquid, at 10 bar. This pressure here is 10 bar. So it is at 10 bar. So your H1 is 10 bar 763. Okay, HF is your H1. And then your SF would be your S1. So 2.138. This and this. Okay, for saturated liquid. Because F refers to saturated liquid, yeah? Don't forget. Then you can move to state point 2, point by point, okay? So point 2 is dry saturated vapor at this pressure, that is 10 bar. So we refer to 10 bar here, also again. But then this time is dry saturated, so it refers to Hg and Sg only. So the H2 for this is equals to your Hg at 10 bar. So Hg at 10 bar, sorry, this one, 2778. And S2 is actually your Sg, 6.586. Okay, dry saturated, 0.2. Now, 0.3 is wet. So now, for wet, let us find out the dryness fraction first thing. So how to find out the dryness fraction? Now, based on this, S2 equals to S3. So we know that at state point 3, where you have S2 equals to S3. And we know that S3 is equals to S2, which is 6.586. S3 equals to S2, which is 6.586. Then, the dryness fraction formula that we have is S3 equals to SF3. This is only for those inside here, wet vapor. SF3 plus X3 SFG3. We apply the formula here to find out the dryness fraction. To find out the dryness fraction. So 0.87. Okay, is 0.87. So once you have found out the dryness fraction, find the enthalpy. Find the enthalpy. Hold on for a while, yeah. Okay, so once you have found the dryness fraction, now you can take the enthalpy formula for wet vapor, H3, HF3 plus X, HFG3. So fill it in and you got your H3. Then for state point 4 here, again, S1 equals to S2, you can also find out the dryness fraction. Okay, this is the formula. Your S4, your SF4 at pressure 1 bar, okay, 1.303. SFG at pressure 1 bar, that is 6.056. So you will be able to find out the dryness fraction. Once this is done, substitute the dryness fraction into the enthalpy formula, which is this. So you got your X, and now HF, that is at pressure 1 bar. So you have 417 and then you have your HFG. No need to take Hg minus HF. Straight away take HFG. So you got your H4. So after that, and when everything has been done, that means you have got all your H1, H2, H3, and H4. Then you can find out what is your heat supply. So your heat supply should be H2 minus H1. Okay? Then your turbine work should be H2 minus H3. Okay? Then your condenser, that is your heat rejected, they ask us to find the energy, okay, in each of these devices here. So the condenser, there is H3 minus H4. Then for the pump here, you have H1 minus H4. So you've got everything here. Then actually we can find out the thermal efficiency or the cycle efficiency actually. Then since they ask us to prove the formula of 1 minus TL, 1 minus TL over TH based on Carnot cycle efficiency. So that is why we also use this formula in order to find the heat supply. That is the area under state point 1 to 2, the process path of state point 1 to 2, this area here. Then find out this area as well. That is for heat rejected. So once you got heat supply and heat rejected, actually you can find out net work. On your net work out, you can straight away take out heat supply minus heat rejected from here as well, or work out minus work in as well. Now I repeat once more, your net work out, you can take heat supply minus heat rejected, or you can take work out minus work in. You should get the same amount of net work out. Or you can use this to calculate your heat supply and heat rejected. Okay, then to find out your net work out. Then this would be your thermal efficiency based on this. Now, if you base on the Carnot cycle way of solving your cycle efficiency, okay, you can prove, okay, by taking TL and TH, remember must add with 273. So you have to prove that based on this and this, the thermal efficiency will be the same. Okay. Thank you for now. Okay. So I will stop on this, or I'll stop from here onwards. Okay. So thank you and bye. Thank you. The second example for Carnot cycle. So a steam power plant uses the Carnot cycle. The boiler puts 25 kilowatt of heat into the cycle and produces wet steam at 303.3 degrees C. The condenser produces wet steam at 50 degrees C. So assuming a mass flow rate of 1 kg per second, and then calculate the thermal efficiency, power output of the turbine, and heat removed by the condenser. So this is the schematic diagram and the TS diagram. And this is a table which I have filled it out for you. So you can refer to your property tables. So based on 50 degrees C, the pressure that we have will be 0.1233. And then based on the temperature of 303.3, that would be at the pressure of 90 bar. So this would be the HF, enthalpy for saturated liquid, and the enthalpy of dry saturated vapor. And this is the entropy of saturated liquid and the entropy of dry saturated vapor. So for Carnot cycle, it's just simple that you take the thermal efficiency, which is net work over heat supply, or that also can be found by taking the Carnot efficiency formula by putting in your lower temperature and the higher temperature plus 273. Okay, so this should be 303.3, yeah, times 100. So you got approximately 43.63% for the thermal efficiency or the Carnot efficiency. This one I remind again, 303.3. Okay. So once you have got that from your network, okay, from this thermal efficiency, which we have found, and it is actually defined as network over heat supply times 100%. So what the question wants us to find is, firstly, is the power output of the turbine, which is the network out. So the network out, what we have is this 43.63 times 25. Then you can divide it by 100 to get 10.9 kilowatt of power, because the heat supply they have given us 25 kilowatt. Then after that, heat removed. So since network is equal to heat supply minus heat rejected, so from this we will be able to find out the heat rejected. This is a much simpler workings. Okay, so that's all for this week, and see you all. Bye bye during next lesson. Stay safe.